Hello again, it's time for physics. This is video lecture 23.5 part 2, where I'm going to talk about the material in chapter 23, section 6. So I mentioned at the beginning of section 4 that the main reason we find Gauss's law useful, one of the main reasons, I won't say the only, one of the main reasons, is that if we have a charge distribution with a lot of symmetry, so much symmetry that just from that we can deduce the direction of the electric field produced, then we can choose a Gaussian surface that mimics the symmetry of the electric field. And when we apply Gauss's law, we'll be able to get a simple formula for E, the electric field. But this process only works if the charge distribution producing the field has a lot of symmetry, and there are only three geometries for which there is enough symmetry. Cylindrical symmetry, very long cylinder with charge, that was section 4. Planar symmetry, infinite extent, planar, flat sheet of charge, that was section 5. And now we say for last, the most symmetric charge distribution of all, spherical charge distribution. And that's what I'm going to talk about in this video. And I'm actually going to start by using Gauss's law to prove two theorems about spherical shapes and electric fields. They're called shell theorems because they have to do with spherical shells. Let me state the first one and then show you how we're going to use Gauss's law to prove it. But the theorems themselves are very handy when you're dealing with the electric field of spheres. So shell theorem number 1 says this. We have a shell of uniform charge. Let's be clear about what we mean. We mean a sphere with a thin layer of surface and then hollow inside. That's a shell, as opposed to a solid sphere, kind of like a bowling ball, if you don't worry about the finger holes, okay? That's a solid sphere, a bowling ball. That's not what we mean when we say shell, okay? We mean just that, a thin spherical surface, usually pretty thin, with a hollow interior. So it's often, well, who knows what it's made of, okay? But it's got a hollow interior. That's what we mean by a shell. So we're starting with a shell that has charge smeared out uniformly across its surface, around its surface. Such a shell will either attract or repel a charged particle, depending upon that particle's sign. If the particle is outside of the shell, that's important, outside, as if all the shell's charge were concentrated at its center. Let me try to draw you a cartoon picture of what this says, because it's really quite amazing. I'll draw it up here at the top. I'll try to make it small enough. So that looks like a circle, somewhat. That's supposed to be a spherical shell with a hollow interior. And it's got some net charge, let's say plus Q, that's smeared out evenly over its surface. And then someone has come along with a point particle, let's say big Q. Doesn't matter, right? And I want to know the electrostatic force that's going to be acting on big Q. From what? From the Q of the shell. Well, if you start to think about it in any real detail, you're going to start to get a little bit intimidated, because you're going to say, well, I guess I have to imagine breaking up the shell into little areas, little patches of area dA and charge dQ, and then figure out and treat that as a point particle, and then figure out the force on big Q from just that. But then I got all the other forces from all the little patches, and I got to add them all up, and they're all vectors. What a mess. The shell theorem bypasses all that. And it says that all you got to do is imagine collapsing the shell down to a point at its center with all the charge that the shell had. And then you're good to go. Don't worry about the shell anymore. There's just the big Q and the particle little q. That's a very useful result. And now I'm going to prove it. And I'm going to use Gauss's law to do it. Now the drawing I've got here I took from your book. And I'm not quite sure why they draw this one this way, because they don't draw any other charge distributions quite like this. But here's what they're saying. Basically what I just drew. You've got a spherical shell that's got a total charge Q smeared out over its surface uniformly. And I'm just going to draw over where they've got it. They're representing the shell by a bunch of dots. That's what I don't quite understand. So I'm just going to draw a circular line where the shell is. That's supposed to represent the shell. And the shell has a radius, let's be very clear, big R. Okay? That's the radius of the actual shell of charge, and that's real charge on a real spherical shell's surface. You could touch that thing. You could reach out with your finger and touch it. Okay? That's the charge distribution. It is on the surface of a spherical shell. Very thin shell. Radius, big R. And they're assuming, by the way, that the Q that's spread out uniformly on that shell surface is positive, just so we have something specific to imagine. Here's what we have to be able to deduce. From that spherical symmetry of the charge distribution, what can we deduce about the electric field it produces at a point, say, outside the shell, like maybe right there, at that point in space? Well, because a sphere looks the same from whatever angle you look at it from, the electric field has to just point radially away from the center, straight out along a radial line from the center at any given point. So that place where I put that dot, the electric field from that has to point straight out radially away from the center of the shell at that point. If I were over here and I wanted to know the direction of the electric field vector, it again would be radially away from the center of the shell at that point. That's the only thing that makes sense, as opposed to, let me draw another one. Let me draw a dashed line out for reference. Let's pick that point. And suppose you could argue, well, maybe the electric field at that point points like that. Not just radially away, that would be that way, but kind of askew at an angle. And the physicist says, but there's nothing physical to warrant that, because the electric field looks the same from absolutely every angle of view. So why would the electric field that I've just drawn favor leftward versus rightward? There's nothing in the charge distribution that favors leftward versus rightward. So it just, on symmetry reasons, can't be an electric field like that. It's got to point at every location radially away from the center of the shell. Is that clear? That's the important point. That's going to be the direction of the electric field. That's how we're going to talk about it. Now, the magnitude of that field can depend on one variable only: the distance that you are from the center of the shell. So here we are at these points that I've marked with the black dots. They're on a surface S2 there. The only thing the magnitude of the electric field can depend on is the radial distance, little r, from the center of the sphere out to that S2. Remember, big R is the radius of the shell itself. Okay, so the electric field must be directed perpendicularly away from the center of the shell, and its magnitude can depend only on the radial distance, little r, from the center. With that in mind, we now choose a Gaussian surface to take advantage of that symmetry. So the obvious choice to make, don't overthink it, is a Gaussian surface that's shaped like a sphere, centered at the center of the shell. And you'll see that in cross-section, this figure shows two such Gaussian spheres. They're drawn as red circles, but they're really red spheres. S2, which is outside the shell, and S1, which is inside. We're going to look at those one by one. Okay? Now, our first task is to derive a symbolic expression for the electric flux through the Gaussian surface that we pick. We're going to pick S2. And it's going to be in terms of the magnitude of the electric field E and the dimensions of the Gaussian surface, as we'll see. Okay, so the Gaussian surface labeled S2, okay, which is a sphere of radius little r that's bigger than big R. That makes sense? That's what I'm talking about. It's outside the actual physical shell. Let me draw it down here. There's the center of the shell. Well, the center of everything. Now this has radius little r. It's S2, not the shell. Now the electric field, I'm going to imagine a little patch of area right there. And the electric field from that points radially outward, as we've talked about. That's the E. And the little area vector for that shell, dA, also points radially outward, right? Perpendicular to the surface and outward. So then as we think about calculating the electric flux through that closed Gaussian surface, we're doing the integral of E dot dA. Let's remember what a dot product means. Magnitude of E, magnitude of dA, cosine of the angle between the E and the dA. There's the picture that shows them. They're pointing in the same direction, right? So that's the cosine of 0 degrees. Remember, the cosine of 0 degrees is +1. And now let me write this using a little bit of shorthand as the integral over the closed Gaussian surface. That means the magnitude of the electric field and the magnitude of the little area patch for that place that I've got drawn there. But in fact, I've got to do this over the whole surface, don't I? For all the little patches dA over the whole surface. Here's the important thing. Since the magnitude of the field can only depend on the radial distance from the center, that's the little r in the picture, every point on the spherical Gaussian surface is the same distance from the center, little r. So every point on the spherical Gaussian surface has the same E magnitude. And so, and this next step is crucial, I am justified in bringing the E magnitude outside of the integral. If you can't do this step, if you can't choose a Gaussian surface in a given problem for which doing that step is allowed, then Gauss's law is not going to be very useful. Because that integral that remains is what a physicist would call trivial, once you understand what the symbols mean. It says take the magnitude of E and then take all the area, take the area of every single little patch on the surface and add them up. Well, won't you just get the total surface area of the sphere? So you'll end up with the magnitude of the electric field times the total surface area of that Gaussian sphere. And again, when it comes to basic geometrical shapes, a physicist or engineer or a mathematician ought to just have some basic geometry in their head, like the formula for the surface area of a sphere of radius little r. It's 4 times pi times little r squared. And let's number that equation, 1. Because that is our symbolic expression for the electric flux when you have spherical symmetry. That's what we've got here, right? All right, that's an important part of Gauss's law, the expression for the electric flux through the chosen Gaussian surface. The other important thing in Gauss's law is the Q enclosed, the total charge inside the Gaussian surface. So here we go. Let me bring that down so you can see that better. All right. Well, I guess we are missing the expression for Q enclosed, so I'm just going to write the question right up here. What is Q enclosed for the Gaussian surface S2. Go back up to the picture of the shell. I'm looking at the Gaussian surface S2, spherical Gaussian surface S2. The shell is, you see where it is? I can also draw it down here. There, that's the spherical Gaussian surface S2. Now let me draw the actual physical shell, the thing you could touch. It's there. That's the physical shell that you could touch. But doesn't it have the charge? Q spread around it? Okay, so what's Q enclosed for S2? It's the total charge of the shell, right? And that's what the problem called that little Q. So that's what the Q enclosed is. But it means the total charge of the shell. So now we'll call that equation 2. And now we'll use Gauss's law. We combine the symbolic expressions for electric flux, that's equation 1, and enclosed charge, that's equation 2. Let's see what we get. So we have E magnitude times 4 pi little r squared equals the total Q of the shell over epsilon 0. And solve for E. So it says, right? Solve for E. We're using the Gaussian surface S2, where little r is greater than big R. So we get E equals Q over 4 pi epsilon 0 little r squared. Right? That's how we solved it. Now you just pause and you look at that and say, ah, but wait. That's the formula for the field of a point charge, right? Q, if it's at the center of the shell, right? And that's what we wanted to prove. That's shell theorem number 1. If you have a spherical shell of charge and you want to know what's happening with the electric field outside, all you got to do is take the shell and collapse it down to a point at its center and put all the charge there. And then just use the formula for the electric field of a point charge. Can't get much easier than that. Okay? Now we do the same thing for the Gaussian surface S1. Let me remind you what that one was. Remember where that one was? In our picture, it's getting pretty busy now. It's the inner sphere right there, inside the shell, right? Now, the spherical symmetry formula for the flux that I labeled equation 1, that is purely the same because it's a spherical Gaussian surface. So you just have the exact same expression. What's different for surface S1 with little r less than big R is what the Q enclosed is. That's my question to you. What is Q enclosed for Gaussian surface S1? Again, picture where the Gaussian surface is and where the shell is. Did you visualize that you've got the actual shell of radius big R and the Gaussian surface S1 of radius little r is inside that. Little r is less than big R. So question, how much charge is enclosed in this Gaussian sphere? Don't overthink it. Is there any charge inside S1? If you said no, then the Q enclosed is 0. All right, then go to Gauss's law. All right, I'm not going to skip any steps here. Phi electric equals Q enclosed over epsilon 0. Use equation 1 for phi electric, and you use 0 for Q enclosed. And so you have E magnitude times 4 pi little r squared equals 0. Well, divide by 4 pi little r squared, and you have E equals 0. That's the result. Okay? Now, I could have picked a Gaussian sphere, the S1. That little r for the S1 could have been anything between 0 and big R. And so by imagining a spherical surface S1 that has a radius ranging from 0 to big R, I can sample the entire interior space of the shell. And I would still always come to the conclusion that E equals 0. And so the point is, the field in the inside of the shell, the electric field at the inside of the shell, is 0 at every point. Okay? This is true at every point inside the shell. That is true. And that means we have just proved shell theorem number 2, which I will now state. If a charged particle is located inside, that's important, inside a shell of uniform charge, there is no electrostatic force on the particle from the shell because there's no electric field inside the shell, from the shell. Okay? So that's also going to be very useful. Right? If you've got a certain shell of charge and somebody comes along and asks you what the value of the electric field is at some point inside, immediately, 0. And it's not hard to get the answer if they ask for the electric field outside the shell. Just collapse the shell to a point at the center and treat it as a point particle. All right, now I'm going to use shell theorems 1 and 2 to figure out how to calculate the electric field, both inside and outside, a solid sphere with charge smeared throughout its entire volume. So now I am imagining a solid sphere, like a bowling ball, if you ignore the finger holes. Okay? A solid sphere that has charge spread all throughout its volume evenly. Let's calculate the electric field outside, at any outside point and any inside point. Note, by the way, it can't be a conducting sphere if I'm talking about charge spread out inside a volume, because you can't have that in a conductor. Charge is going to be on the surface. So this must be a non-conducting solid sphere, an insulating sphere. Maybe it's made of plastic, for example. All right, so here's the next key idea, building on shell theorems 1 and 2, as I will explain. We want to find the electric field outside a solid sphere, solid, not a shell, a solid sphere of radius big R with uniformly distributed total charge Q greater than 0. And again, for some reason, they are representing this spherical distribution of charge as a series of dots. And again, I don't know why. So I'm just going to draw the surface of this sphere as best I can. It's not easy drawing on these pads. Okay? And emphasizing that the charge is spread out uniformly throughout that entire volume. And that's an actual sphere, and it's got a radius big R, and you could touch that thing. It's a real physical sphere. And our task is to find the electric field at any exterior point outside. So what they've done here is they've chosen a spherical Gaussian surface. That's the surface drawn in red. And it has a radius out to the Gaussian surface of little r, where little r is greater than big R. The Gaussian surface is outside the solid sphere. It completely contains and surrounds the solid sphere. Our task, we're going to use shell theorem number 1 to get the result for the electric field at a distance little r greater than big R. So I'm going to explain to you how you can use shell theorem number 1 to do it. Remember, shell theorem number 1, shell, says that if you have a spherical shell of a certain radius and a certain total amount of charge, and you're at an outside point from the shell, then to find the electric field at that outside point, you can just collapse the shell to a point at the shell's center with the total charge of the shell. So here's what you do. You do a thought experiment. You imagine, there we go, sorry. You imagine breaking up, dividing up the solid sphere into an infinite number of infinitesimally thin, nested, spherical shells. I'll draw one of them. And I'll even shade it in so that we can be clear where it is. Okay, now that's one shell. You have to imagine a whole bunch of them all nested, starting at the very center and working your way out so that you fill in the whole solid thing. And this shell has some total amount of charge, I'll just call dq, over its surface. Well, for that shell, if I want to know the contribution to the electric field at a point right there, say, which is outside, I just collapse the shell to a point at the center. dq now would be at the center, and the electric field dE from that would have a magnitude of dq over 4 pi epsilon 0 little r squared, because I will have collapsed the shell to a point particle right there at the center, which is a distance little r from this point. Now that's that one shell. So you just do the same thing for all the shells, starting at the center and working your way out. But when you're done, you'll just have the total E at that point, and it'll be from the total charge. Right? Just so the net result will be that the electric field, so for little r greater than big R, that means we're at an outside point, right? The electric field magnitude is just the total charge of the whole solid sphere over 4 pi epsilon 0 little r squared. And that actually will work for r greater than or equal to big R. Since it's not a conducting sphere, you can even go right down to the surface big R. Okay? All right, it's that simple. Now, I do want to just tell you, don't overthink that. Use that, right? If you've got a solid sphere, now it's got to have the charge spread throughout its volume uniformly, then you just collapse, okay? All the charge to a point at the center, and use the formula for the point charge. Easy. Okay? All right, now, a little bit more challenging, because we want to know this too. Next thing, next key idea. Find the magnitude of the electric field inside the solid sphere, inside the solid sphere of radius big R with uniformly distributed total charge Q. Inside. So now, remember, the surface of the actual sphere big R is out to there. And now we've picked a location inside this solid. And we want to know the electric field there. Okay? So now we've chosen a Gaussian sphere. Again, we'll draw it in red. That's inside the solid. Let's give it a radius little r. Notice then little r is less than big R. And here we are at a point right there on that Gaussian surface, and we want to know the electric field. Magnitude. We already know the direction, perpendicularly away from the center. All right, how are we going to do it? We're going to use shell theorems 1 and 2, as it says there in the next bullet point. Using shell theorems 1 and 2, we're going to get the result for the electric field at E. Get that just a little bit higher. That's fine. At R, little r less than big R. All right. First, from shell theorem number 2, guess what? All the charge, I'll shade it here, all the charge of the solid sphere, that is between the solid sphere's surface and the surface of our Gaussian sphere, that's the part I just shaded. All that charge is outside the Gaussian surface, but still in the solid, right? All of that charge is outside our Gaussian surface. And from shell theorem number 2, there can't be any contribution to the electric field from that. Because you can think of that outside space as being a bunch of shells nested, but each one of them produces 0 electric field at points inside it, and we're inside those shells. Okay? So we don't have to worry about that charge I just shaded. It produces no electric field where our Gaussian surface is, because our Gaussian surface is inside that. That makes sense? So all we really have to do, let me shade now in a different color, is take all the charge that's inside the Gaussian surface that we've chosen of radius little r, there, that I just shaded in green, and collapse all that to a point at the center and treat it like a point particle. And then we'll have the electric field E at that point I picked on the Gaussian surface. Okay? All right, so the magnitude of the electric field will be the Q enclosed over 4 pi epsilon 0 little r squared. Q enclosed is the total charge inside the Gaussian surface. That I had shaded there in green. It's supposed to look like a sphere. So next, the question is, how do I find out how much that is? Well, I'm going to think about it this way. I've got charge spread out throughout a volume uniformly, so I can talk about the volume charge density of the solid sphere. Rho, which is uniform. And I just multiply that then. I take that charge per unit volume for the solid sphere, and I multiply it by the volume that's inside the Gaussian sphere, the red sphere. That's the V enclosed. So that's rho times, now I need the volume of a sphere of radius little r, volume, 4/3 pi little r cubed. But that does leave us with a little bit of question, though. Well, what do we do with that volume charge density, rho? Because the problem doesn't state anything about that rho. So we can't have a rho in our answer unless the problem states what rho is. Volume charge density. We've got to figure it out from what we do know. Here's what we do know. For the actual solid sphere, total charge spread throughout its entire volume, little q. Radius of that solid sphere, big R. So the rho is Q total over, how do you like that? V total. So Q for the Q total, and for the V total, 4/3 pi, watch out, big R cubed. You see that? And if you want, you can write that like this. 3Q over 4 pi big R cubed. And now let's substitute that expression for the volume charge density, uniform volume charge density, for the rho there in the Q enclosed formula. So we have, for the volume charge density, 3q over 4 pi big R cubed. Really important to keep track of the r's. 4 pi little r cubed over 3. Okay, big R in one place and little r in another. Okay, 4 cancels 4, pi cancels pi, 3 cancels 3. Nothing else cancels, right? So I'm left with q times little r cubed over big R cubed. And now I put that expression right there for the Q enclosed right in there in the E formula. And I will have the formula that will then give me the electric field magnitude at any point in the interior of the solid sphere. Let's see what we get. E equals Q enclosed, Q times little r cubed over big R cubed. I'll write it like this. Times 1 over 4 pi epsilon 0 little r squared. Yes, little r, the radius of the Gaussian surface. Well, I've got a little r squared downstairs. I can take 2 of those little r's that are upstairs. And so I'll do some grouping now. I have q over 4 pi epsilon 0 big R cubed all times little r. And this formula is valid for r between 0 and big R. This is the internal field. Okay? Notice it grows linearly with r. The r is upstairs, and it's not an r squared, and it's not downstairs. It's upstairs. So when you're at any point in the interior of this solid, the electric field grows linearly with r as you go farther out. I do want to show you another way to write this result, okay? Because you'll see this sometimes. Sometimes a problem might indeed not tell you the total Q of the solid sphere, but instead it's volume charge density rho. So all I'm going to do is kind of do a little bit of a reverse here. Now that I've got the answer for E that has the Q total in it, I'm just going to go back up to the formula up here that related rho, volume charge density, to the Q total. And I'm going to solve it for Q total, okay? So Q total equals, just look at the algebra, 4 pi big R cubed rho over 3. And then I'm going to substitute that in my E internal result for the Q. Okay, so this is an alternative way to write the E. E equals, okay, for the Q, 4 pi big R cubed rho over 3. And then I still have a little r upstairs, just doing the algebra carefully, over 4 pi epsilon 0 big R cubed. And I see quite a bit of stuff cancels. And I get then rho over 3 epsilon 0 times the little r that's upstairs. So that's just an alternative way you'll sometimes see the internal field formula. And it's the one to use if the problem gives you the volume charge density of the solid. But if they give you the total charge of the solid, then use the one right up above. Now the last thing I want to do is sketch this field. This is very helpful, very informative, okay? I want to sketch the magnitude of the electric field that this solid creates versus little r, the radial distance from the center. So we'll have E magnitude going up the vertical axis, and little r going out the horizontal axis. Little r starts at 0 and goes forever, going on and on. But one important tick mark on the radial axis is the point that represents the surface of the solid, big R. Because that's where you transition at that point. Right? That's the surface of the solid. And if you are to the left of this point, right here on the radial axis, you're at a distance from the center less than big R, you must be inside the solid. Versus if you're at a point on the horizontal axis out here outward, then you're at a distance little r from the center that's bigger than big R, you must be outside the solid. Yes? So all of this range is inside the solid, and all of this range is outside, and that range is unbounded. It keeps going that way. And what does this electric field look like? Well, when you're in the interior region, you have to use the formula for the interior electric field. I'll use the Q over 4 pi epsilon 0 big R cubed times little r. Here's the key thing, times little r. And when little r is 0, it's 0, so it starts at the origin and it just grows linearly, with a slope equal to Q over 4 pi epsilon 0 big R squared. And when you get to the surface, what does our interior electric field result give? Plug in little r equals big R, and you get this result. Q over 4 pi epsilon 0 big R squared. Just like the total charge is at the center. And you're on the surface, so you're a distance big R from it. Now, for the outside points, for little r greater than big R, you have to use the result from up above, way up here, right there. The external field result. And it's just a point charge, Q over 4 pi epsilon 0 little r squared. So now we're going to sketch that. All right? Note we start at little r equal to big R. Where does that put us on the graph? Do you see? Using the outside result, it puts us at the same place where the inside result ended. The outside result just picks up right at that point. And then it goes down, on and on and on, like 1 over r squared. So this part grows like r, and this part diminishes like 1 over r squared. Very famous behavior, very famous. For the electric field inside and outside, a solid sphere of insulating material with total charge spread uniformly throughout its volume. All right, now I already gave you a class engagement exercise from the earlier video lecture for Monday, so I'm not going to give you another one now, even though I have a practice next. So why don't we just talk through this practice together instead of me assigning it to you? Because it's going to be practicing with the ideas I just talked about here. All right, we are given a sphere of radius big R with uniformly distributed throughout the volume total charge Q greater than 0. Just what I was thinking about and talking about. First question, what is the field magnitude E at the center of the sphere? You see the answer? You can pause the video and think about it if you want. What is the field magnitude at the very center point? Well, did you look at our graph or our interior field result? It's right up here. Interior, the field is proportional to r, the distance from the center. If you're at the center, what's little r? 0. So what's the field? 0. Where did our graph begin when little r equals 0? At E equals 0, right there. Okay, see where that's headed? Electric field is 0 at the center of the sphere. All right, B. If we want to express the field magnitude at the surface, radius big R, which equation for the E should we use? The external equation, the internal equation, or whichever one we want? What do you think? Feel free to pause the video if you wish. Did you say C? You can use either, because as we showed in our graph, When you are at the surface of the sphere, little r equal to big R, the E field formula for the inside and the E field formula for the outside match. They're equal. They agree, because that's where they meet up. Okay? So you can use either. You'll get the same answer either way. That's that one. Next, what is the formula for the field magnitude E at the surface of the sphere? Feel free to pause it if you wish. Well, we actually just talked about it, didn't we? We're now talking about that radial distance. It is the total charge Q over 4 pi epsilon 0 big R squared. And we saw from that graph that I made that that's the place where the electric field has its biggest magnitude, right? That's the highest point on the graph right there, when little r equals big R. So we're going to call that magnitude there that I just wrote down that formula for EM for max, because that's where the field magnitude is biggest, at the surface. That's a very useful thing to remember. Okay, D. In terms of the radius of the solid, big R, at what radial distance is the field magnitude at its maximum value? Well, what do you know? We just said, didn't we? Little r equals big R. That was easy. All right, E. And in terms of that maximum field magnitude, E max, what is the field magnitude E when you're at half the radius, right? Little r equals 0.5 R. Think about that for a minute. Come back. Okay, did you think about it? Did you get a result? So we are at, here's a way to write it, big R over 2, right? Or 0.5 big R. That's the little r. What's the E? Well, first of all, note, that's an interior point, right? That's an interior point. So you got to use the interior field result. Be careful to use the correct one. So that's Q total over 4 pi epsilon 0 big R cubed times little r, 0.5 times big R. That's the little r value. So actually get one factor of that canceling, and you get E equals 0.5 times Q over 4 pi epsilon 0 big R squared, but that quantity in the parentheses is what we called E maximum. So the answer is that the field is half of E maximum, when the radius is half the maximum. Well, that would just correspond up here to going roughly right about there, right? That's roughly at little r equals half big R. The graph, go right there. And that's roughly half of the maximum field. Okay? All right. So, spherical distributions are very important, especially in atomic and molecular physics. And so the class on Monday will be talking about cylindrical and spherical charge distributions and applying Gauss's law. Okay? All right, that's all for this video.